So what we want to study is not really single fields, but one field contained in another field, what are called field extensions. Like fields f and k, where f is contained in k. That's what comes up when you try to solve equations and stuff. But let's see what fields we know so far. We know rational numbers, real numbers, complex numbers. These fields fp, where p is a prime. And then we learned this rather general tool last time that constructs from any domain S to a field called its fraction field, frac S. This is the construction that gives you Q starting from Z. You can apply this to other rings like Z adjoint square root 2. This is all numbers of the form a plus b root 2, a, b in Z. If you apply this construction, you'll get Q square root of 2. I'll leave you to check. This is all numbers of the form a plus b root 2, a, b in rational numbers. These are examples of fields as well. These are subfields of real number. Similarly, you can define things like Q adjoint I. That's a fraction field of Zi. We can check, etc. You can apply this construction to polynomials in one variable, with maybe even with real coefficient. So these are called polynomial functions. When you apply this construction, frac of Rx consists of all functions like this, where f and g are polynomials and g is non-zero. These are called rational functions. So this is the field of rational functions. I don't have to check anything because I have the fraction field construction. I know that this is a domain, so I know that this is a field. And I have a way of naturally identifying the polynomials inside. In each case, here, 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 there's a natural way to identify the ring on the left as a subset of the field on the right-hand side. So these are some examples of fields that we know. Instead of one variable polynomials, you can take two variable polynomials. Instead of real coefficients, you can really take coefficients in any field. And then there's one more super important construction that we have seen, which is via quotienting. You start with a field f, take the one variable polynomial ring, and you quotient by an irreducible polynomial. And this happens to be a field again. And actually most of the extension fields that we are going to study are going to be of this form. This is the most important example as far as we are concerned. And this is going to be a field that contains f, or an isomorphic copy of f. So if we call this k will be a field that contains f after we do a little mental gymnastics. And these are the kind of extensions that we are going to study. But that was sort of buried in a lot of things that we did when we talked about PID. So I have a sort of review of that here. First, I'm going to collect some facts about PIDs. So R is going to be a commutative domain with 1. A proper ideal is called a maximal ideal if there is no proper ideal that properly contains M. So you have R and you have M. If you find another ideal in the middle, then this guy has to be either M or R. There is nothing strictly in between. I have a way to recognize maximal ideals. A proper ideal M is maximal if and only if when you quotient by it, you get a field. Then we have an equally important notion of a prime ideal. An ideal is called prime if whenever A times B is in P, either A is in P or B is in P, for all A, B in R. These are generalizations of prime numbers. A non-zero element is called a prime element if the ideal that it generates, the principal ideal that it generates, is a prime ideal. I think earlier when I talked about it, I might have missed this non-zero part. let's assume that. That would make things cleaner. We have a similar recognition lemma for prime ideals. A proper ideal is prime if and only if, when you quotient by it, you get a domain. An immediate corollary of 1 and 2 is that maximal ideals are prime. Because when you have a maximal ideal, when you quotient by it, you get a field. A field is certainly a domain, so you got a domain, which means the thing was a prime. Okay. But the converse is not true in general. There are prime ideals that are not maximal in general. But if you are in a PID, then every prime ideal in there is maximal. That's lemma 3. That also we proved at some point. And then we have this fourth lemma, which talks about prime elements and irreducible elements. An element is called irreducible. A is irreducible if you don't have a proper factorization of A. So whenever you write it as a product of two things, one of them is a unit, meaning invertible in the ring. So for example, 5 is irreducible because the only way to factorize 5 is irreducible in Z, because the only way to factorize it is to pull out a unit. That's not really counted as a factorization. Whereas 6 is not, because there is a proper factorization of it into two non-units, 2 and 3. Okay. And then this lemma here says that prime elements in any commutative domain is always irreducible, and you also have a converse when you are in a PID. So in a PID, the prime elements and the irreducible elements are basically the same thing. Oh, and then I missed this lemma here. It says that non-zero prime ideals in PID are maximal. Oh no, I did say that. That's sort of the converse of this statement holds, that maximals are prime. By the way, again, when we talked about lemma 3 before, I might have missed this non-zero in the part of the statement. When we used the proof, we definitely needed that. I mean, if you take the ring Z, which is certainly a PID, 0 is a prime ideal, but 0 is not a maximal ideal. Here is a ideal that is properly, strictly bigger, but still proper. Yeah. So 0 is an example of a prime that is not maximal in Z. So, but what it says is that non-zero prime ideals are all maximal. Okay. So these are all the results that I want to remember. And now I can state this theorem. It's a theorem about quotients of fx, where f is a field. So polynomial ring in one variable with coefficients in a field. So first thing to remember is that this is a PID. That sort of makes it, that's what makes everything work. That's why we collected all these facts about PIDs. So every ideal in this ring fx has the form parenthesis little fx for some little fx in capital Fx. It's generated by a single polynomial. And the theorem gives 5 statements that are all equivalent. So you take a non-zero polynomial in capital Fx, call it little fx. Then the following 5 statements are equivalent. F is a reducible polynomial. That's same as saying that the ideal that f generates is a prime ideal. That's same as saying that when you quotient by it, you get a domain. That's actually turns out to be equivalent to saying that ideal generated by f is actually a maximal ideal. And that's equivalent to saying that when you quotient by f, you get a field. So in particular, what this is saying, if you look at 1 and 5, if f is a reducible polynomial, in one variable polynomial ring with coefficients in a field, then fx mod the ideal is a field. And we'll see that this field naturally contains a copy of f, or an isomorphic copy of f. In other words, it contains a subfield which is isomorphic to capital F. So in that sense, this field is a field that contains f. And these are the kind of pairs of fields that we will study. Let's see how this theorem follows. Actually, everything that we need is collected on the left. It's all done here. So 1, if and only if 2 follows from this lemma 4 down here. Irreducible polynomials exactly are the irreducible elements in capital Fx. And irreducible elements are the same as prime elements because you are in a PID. Okay. The equivalence of 2 and 3 is just recognition lemma for prime ideal, lemma 2 follows from lemma 2, right? Equivalence of 2 and 4 follows from lemma 3. Maximal ideals are certainly prime, and we are talking about non-zero polynomials here. So the prime ideal that it generates, if you take the ideal f, that's a non-zero ideal, so that's a non-zero prime ideal. And then non-zero primes are maximal. That's what lemma 3 says. Okay, and then equivalence of 4 and 5 follows from lemma 1. So much of the work we did with PIDs and ideals in PIDs give us this when you apply it to this PID, Fx. Okay. And the last thing I want to say is that you can identify f inside Fx mod f. So assume f has degree at least 1. Not necessarily irreducible even. If it's irreducible, then it's certainly degree at least 1. Now this we have already identified inside f of x, you see, as degree 0 polynomials. The constants have already been identified as the constant polynomials. And then from fx to this quotient, you have the quotient map. The map that takes an element to the corresponding coset. So if you combine these two maps, you get a map that takes A to its corresponding coset. And I claim that this is a injective map. This is injective. Because it's a non-zero map. And it's a homomorphism because both these arrows are ring homomorphisms. Ring homomorphism. So this is a little remark I don't know if I made before, but non-zero ring homomorphisms from a field has to be injective. Because whenever you have a non-zero ring homomorphism, the kernel is an ideal, but the only ideal in a field is the zero ideal and the whole field. So if it's a non-zero map, so the kernel of this map, let's call this map I, is not the whole thing. So the kernel has to be just 0, which means I is injective. Why is this map non-zero? Because a constant goes to the constant, the coset of the constant. So in particular, like 1 goes to the coset of 1. But 1 is not a multiple of f because f has degree at least 1. So this is not equal to the 0 element of this ring. Call this k. And this is not 0 of k. One plus f is not the 0 of k. But this is I of 1. So that tells you that this map is injective, and that allows you to identify, we identify f inside this ring via this map.